Hey class, here is our explanation of my notes, and I'm going to go through them. I'm going to flip around some and show you different things, but hopefully by the end of this you'll feel good about it. So we're going to start with Green's theorem, and this is all just some setup for it. So back in an earlier section, we showed that when F is a conservative vector field, then any circulation came out to be zero. And that was true from the fundamental theorem of line integrals, or the fundamental theorem of conservative vector fields, in that if you want to find the circulation or even any line integral over a path, all you have to do is the potential at the end point minus the potential at the starting point. And so that is how we get zero, because the end point and the starting point are exactly the same. So Green's theorem will tell us about circulation when F isn't conservative. And so you have a way of doing it, and it's what I call the old way, where you have to parameterize the curve, and then you feed the curve into the vector space, and then you take the tangent vector for the curve, and then you dot the two, and then you use the bounds on the parameter variable to actually integrate. And in this case, we need what's called a simple closed curve. And all that means is it's a curve that doesn't intersect itself. So if you're running around like this, if you're up and in and up, and even if you do this, as long as it never crosses, right here it crosses itself, so this is not a simple closed curve, but this one is. All right, this notation, it looks like the partial derivative d, but it stands for the boundary, and that boundary of d is a boundary of a domain. And so but the boundary is a curve, and so the surfaces, they're not infinite. If they were infinite, we would have infinite line integral values or surface integral values, etc. And so the surfaces aren't infinite, and for that reason, they have an edge to them. And whatever that edge is a curve. So around the outside is the curve, but it's also the boundary of that region. And so there I said the curve itself is equal to the boundary of D. Now, we want counterclockwise orientation. And the thing is, I think this is where we measure counterclockwise in trig and our parameterization for a circle using cosine t and sine t naturally makes it traverse counterclockwise. In here, we want counterclockwise also. That's called the boundary orientation. And we always want counterclockwise orientation to be positive. And so the way that you can tell is, if you thought that you were walking around this curve, you ask yourself, where would your right hand be? And as long as it's outside of that piece, then you're doing it right. What I have written here is you want your left hand to be in that domain as you walk around. So if you think about walking along this curve here, this is my left hand, and it would be inside of that piece. And the whole time I walk around, that is the case. So then, this is just to recall that a way of writing the vector line integrals, there was a way of doing it a little bit differently. This was in my notes earlier also. This is just the parameterization for a curve. Any curve, we can give it an x function and a y function. We get bounds for whatever the parameter variable is. And then this comes from really back in 1a. You know that dx dt is x prime of t. And so it kind of looks like if you multiplied that dt over, like it would have been right here. And if you multiplied both sides by dt, you would pop that dt on there, and the dt's would cancel, and so you would get it. So then all I've done is I've taken this, and I've seen then f1 dx, if that's dx, then that's f1, feed the curve, and then we have the x prime. And then f2 dy, here's dy, so we have f2 of the curve right there. and then dy is y prime dt. Since this has the exact same bounds, it should be an integral for that dt and one for the other, but the bounds are the same because the functions are coupled in that parameterization. So all of this is kind of review, notation, setup, and the like. So what does Green's theorem say then? Green's theorem says, let D be a domain whose boundary, the boundary of D, is a simple closed curve, oriented with the boundary orientation. So all of those have to be satisfied. Then, if you want circulation through that vector field on some curve, you can find it by using a double integral and these partial derivatives in here. And so somehow it works out. I'd say here the proof is on page 1004. I'm going to show you this. It is right here. So here's the proof. And it is pretty technical. They say right there in the beginning it's quite technical. What's more important for me is that you know how to use and apply the theorem. If you want, I can talk about this in office hours. I could do a separate video on it. I don't think it'll be super useful for getting you through your homework. But there are proofs of this. It exists. There's videos of it. And what I'd rather do is show you how we actually do problems. So here's our first problem. They give me this line integral here, and they tell me C is this triangle, and it's got vertices at 0, 0, 1, 0, and 1, 1. So we go 0, 0 to 1, 0 to 1, 1, and then we're going to go back closed, and so that circle there means it is a closed curve. And so if I used Green's theorem, now here's the thing. Let's forget this. Let's do this the old way, okay? So down here I have the old way. The old way, here's the problem. This is one curve, this is one curve, and this is one curve. And so notice I have a C1 curve, a C2 curve, and a C3 curve. Those all have to be parameterized. On here, what I know is that any point on here is x comma 0, because we haven't went up or down. And so if I made it t comma 0, and if that's really 1, I can let t go from 0 to 1. And so that's what I've done there. And so you see how I get that. Then once I have that, I need to feed it into my vector field. And so I pulled the vector field out there. So then I do the f of c of t and put those in. I figure out what c prime of t is, and then I have to dot them. Now that stays on hold, but for this curve right here, I'm going to use this function with these, with those limits of integration. That is right here, folks. Then we have the second curve, and that curve is right here. And the problem is that we hit this right angle here where it's not differentiable. And so we don't have a way to just instantaneously change direction there. It has to be some sort of a continuous movement. So on here, I know any point here looks like 1 comma y. And I know y goes from 0 to 1. So if I made it 1 comma t, that's right there, that would work to parameterize this line. And I didn't say this, and it's coming down here, and I already know it, but one thing you should do also is just check. When I put in 0, I'd be at 0, 0, so I'm there. When I put in 1, I'd be at 1, 0, so I'm there. So I start there and end there. Yeah, that's the right way. And here, in this, when I put in 0, I'm at 1, 0, so I would be right there. And when t is 1, I'd be at 1, 1. So this is 1t in there. And there's a comma. But we'd be at 1, 1, which is right up there. And so we go from there to there. Yeah, that follows the orientation. Okay. So now I have a second curve. I need the tangent vector for that curve. I have the bounds for the curve. I need to feed that curve into the vector field. And then I have this function with these bounds, and that's right here. So that gives me one piece, two pieces, but I'm not back to where I started yet. So now I have to parameterize this piece. And that is nothing more than the line y equals x. So any point on here looks like x comma x. So I could make it t comma t. And then I'm going to go 0. So then it'll be to 0, 0. And then when t is 1. Now watch this. So I have the tt there. And this is what I was trying to say before. When I plug in 0, I'm at 0, 0. So I start there. That's my start. And when t is 1, I'm at 1, 1. And so I start here, end here, which means I go that way. That's backwards from the orientation. And so we have the wrong orientation. Well, if you go against the orientation, you put a negative in front of the integral. So it should be one integral plus another integral plus a third integral, but that third integral is going to have a minus sign, and notice there's a minus sign down here in my work. That minus comes from the fact that we are going against the orientation in that case, so we correct for it. And but once I have this, we find our tangent vector, we feed the curve into the vector field up there, we take a dot product, and we get this this integrand here. So I have that integrand with those limits. That's right here. We have the negative we already talked about. So I have 1 to do, 2 to do, 3 to do, and you work all of this and you get this answer, okay? That's the way that I believe you all would know how to do it right now. And it uses nothing but the preliminary work from the vector line integrals and conservative vector field topics. Now, using Green's theorem. Green's theorem says, if you want that, forget all that. Make it a double integral, figure out these derivatives, and then just use the entire domain for it. And so, in here, if you look, so what I need is, I need the derivative of the second function with respect to x. Now look, the second function is what goes with the dy, so I need that one with respect to x. This with respect to x is 0. So that's a constant, and so it's 0. And then I need a minus the derivative of the first function, and that goes with the dx, with respect to y. And there's a minus there on it too, okay? So the derivative of this with respect to y would just be e to the 2x plus y times 0 plus 1. The derivative of 2x is 0, and the derivative of y is 1. So that is that piece in there. So I would have done that in class on the board. I did it for you in my laser pointer, and but that is figured out from this, and that's how we get that. The minus is right there. So this was 0 minus the e to the 2x plus y. And that minus is a constant. I can pull it out. And so it's right there. And then look how easy it is to encode this domain. In this domain, if I go dy first, then dx, well, y goes from 0 to the line y equals x. So it runs 0 to x. And then x gets the whole gamut. And the whole gamut is it goes from 0 to 1. So we do that. Now we just have a simple double integral. And that double integral, guys, when you work it out, and I mean, just trust me on it, you can do it if you want, but that answer and this answer are identically the same. And I would argue that this is much easier way of doing it than the old way, because the old way I had to parameterize piece by piece, and from there I had to still find tangent vectors, still plug the parameterized curve into the vector field, and then after I did all that work, 1, thinking of a parameterization myself, 2, finding the tangent vector, that's not that hard, 3, plugging it into the vector field to see what the parameterization looks like in terms of the vector field, and then 4, I still have to do a dot product, and 5, then I still have to do actual integration. And so that's a lot of work. And this I had to do 3 times because there was 3 pieces to it. Whereas this, it was one integral, and I was done. This takes barely a quarter of a page, where this takes the better part of half of a page. So I would say this does make life easier. All right, a really cool thing, and it's kind of near and dear to me. I'm gonna nerd out here for a second and tell you about it. If you consider this very specific vector curve or vector field, negative y comma x, and let D be any domain bounded by a simple closed curve, then what is true is the derivative of the second function with x is 1. The derivative of the first function with y is negative 1. And when you subtract them, this is the integrand from Green's theorem. That piece, then, the integrand is just 2. And so, then what I know is this. If I do this integral right here, it comes out to be 2. So when I have the 2 in there, I can pull it out. And when you do a double integral and the function is 1, remember back in the day, no matter what your patch is, if above it the whole thing is 1, then you're going to have just the base area times the height, and that would be the volume. And so this will give you the area in that case. And so on the floor in there, when you do a double integral of 1, you get the base area times the height would be 1, and so you would just get the base area. So that's that piece right there. So the height of 1 does give you the bottom and then a plane that is 1 off the ground, but the volume of this thing is the base area times the height. But if the height's 1, then it's just the area of the base, but the base area is the domain. So that's how you get that. So then if I divide this side by 2 and put a half over here and ignore that stuff in the middle, and I lead with that, so that area of D then equals, and when I divide the 2, this piece is over there. So that, right now when you say it, you go, that's kind of cool, I guess. But I guess I don't really care. You guys, you really care about this, and here's why. This says I can use calculus to find the area of any shape. Literally, if I took the plane and I said, I want to know how much area is in this thing, this would find it for me. The honest God truth. And so, I want to show you something else in here. So, on this, that's after that. Right here. So here is that work talking about the area of that. And it comes out that there's something called a planimeter. And a planimeter, it was created a long time ago, and it has this kind of weight right here. It's like a little anchor. It's like a paperweight. And then it has a couple arms on it. And then out at the end, you have a pencil. And literally you draw the pencil around the shape and just trace it. And a planimeter it has these wheels in there. It's blurry, I know. I'm going to show you one on the internet here in just a second. But it has those wheels, and as you move around the shape, it actually adds up and figures out the area for you. So if you just draw with this around a shape, there is a machine called a planimeter, and it will tell you the area of any two-dimensional, simply closed shape. And here is what they look like. And I like the old ones. I don't know why, just because back in the day, they just looked cool. Like, here's one. And this thing, it has gears in there. And all of the gears in that box at the elbow, they roll different ways based on how the pencil moves. And however it moves, when you're done, those gears will tell you the value of that shape, no matter what it is. And that's really cool. And so that's called a planimeter, and it comes from this formula using a very specific vector field and applying Green's formula, and we can actually figure out the area of a certain shape. So that then, and here's something strange. Many of you that took 1B with me, we did the volume of a sphere, and we did it by taking the top half of a circle of radius r, and we spun it around the axis, and then we used the disk method, and we integrated, and you get the volume of a sphere. And that's pretty cool. But you've never seen the derivation for the area of a circle. And I don't know of another way off the top of my head except for this to actually get it. And so here it is: derive the formula for the area of a circle of radius r. Okay, well, I'm going to use this then. And so I need to first parameterize it. And so the parameterization for any circle of radius r is r cosine theta, r sine theta, and because it's one full circle, theta gets to run from 0 to 2 pi. Then I need my dx and I need my dy, and so my dx would be negative r sine theta d theta, and my dy would be r cosine theta d theta. So then in the formula now, and I'm using this formula with the very specific vector field in there, so that's what's right here. I'm using negative y, so there's negative y, and then dx, so there's dx. And it has a d theta, so there should be a d theta here. But what I do is I pull it out, and I make it one d theta all at the end. So there is a d theta there. I didn't forget it. The parentheses show that it's attached to both. And then we have x, which is r cosine theta, and then we have dy, which is r cosine theta, and then the d theta right there. So when I put this together, the two negatives make a positive. We get an r squared there. This gives me an r squared. I'm going to have a sine squared and a cosine squared. When I pull out, sine squared plus cosine squared is 1. And so I find that this integrand, which is the entire thing in there, is r squared d theta for me. So now I know this is r squared d theta. I know the bounds, it's 0 to 2 pi. I can put a half out front, and that'll give me the area enclosed by this curve. And that's the area of a circle. And so I put the half out there, and I feed this in. So there's the half, there's the bounds, there's what we got when we did the negative y dx plus x dy. And when you integrate it out, that half out front kills the 2 right there, and it leaves it pi r squared, and that is the area of a circle of radius r. And so then additivity of circulation. So this is just like what happens if you have like a punctured region or something like that. And this is where it starts getting weird, but in a nerd sense, it's where it gets a little bit more fun. Especially when you think that when you're cutting holes in a surface, that is kind of the idea behind wormholes. And we're cutting a hole in the fabric of the universe, the space-time, and maybe we can tunnel through or something. So let's look at this. And so the way that we do this is we have this one big long curve right here. And what I'm going to do is I'm going to cut it right here, like surgically cut it. That's what this dotted line is. And I'm going to make 2 regions right here. And so one of them we walk across this way. And this is the boundary orientation. So when you're walking, you want your left hand touching. And so as I go around, my left hand will touch. And then that means the boundary orientation has to be that way on there. Now, when I figure this out, if I want the circulation over the whole boundary, I should be able to add these 2 boundaries. and do that. But in there, I'm going to close them off. So I am going to close them off with that piece. And so the question is, does the dotted part make the value wrong? And it's no, because the thing is, really this boundary over this whole thing is just the integral of just the top. So this is just the top piece plus the integral of just the bottom piece. And when I put both of those together, that will be what we get. So when I do the top piece, so now we have this top piece here, that is, and I'm doing it on the entire boundary of D1, that's going to be the regular one across the top. Plus, then we have this line integral of this, what I call the mid curve, the dotted curve. And then when we do it on the second curve, so down here, we have the integral over the bottom. So now we're going to do the bottom, but then we're going to have the integral of the midsection again. And notice one way it's going this way, and then the next time it's going this way. And so the curve on the middle is either oriented left to right or right to left. So one of them has to be positive and one of them has to be negative. And because it's the exact same vector field and the exact same curve, whatever we pick up there, positive, we will give exactly back there, negative. And so it offsets to be 0. And so the dotted line doesn't matter at all in there. And so written it out like longer, you can see, and then we just cancel those off. And so that piece does, in fact, equal that. So you can surgically cut regions, and that helps because if you have a region like this, and look, notice it's that way on the outer one, but it's this way on the inner one. Because when I walk here and I'm walking this way, now my left hand would be over here and I want it to touch the region. If I put it this way, then when I walked I'd be touching there, but this is not there. That's a hole in it. And so in this, both have the right orientation, so the boundary is just the first curve plus the second curve. And what I've shown you up here is you can do that and break it apart and just take pieces of it in curves. Now this one I just did, notice this one, it goes one way and this one goes the other way. This one, when I walk, my left hand is inside, and that hole is not there. So C3 has the wrong orientation. But C1 is correct and C2 is correct, just like over here. So this time the boundary would be C1 plus C2 minus C3, and you need to offset that because you have the wrong orientation on that boundary. Then when you have a region like this that's got a hole in it, we can do the same thing and cut it here and here with surgery. And then I can go around this and I'll pick some stuff up. Then I'm gonna go around that piece, along this, and along that. But when I come back the other way, I will go this way and I'll pick stuff up. Now I'm going that way. And now I'm going that way. So the first time I went that way, the second time I went that way. This is going to offset just like it did before, and this will offset over here too. So if it's cut like that, you can break it apart, and the piece where you cut it will not matter. It's just like how the area of a single value, the integral from a to a of any function, is always 0, because there's no area to a line. But whatever you pick up in flux here, going one way, you're going to give the exact same amount back when you do it the other way. And one way you're going to come across this way, the other way you're going to come across that way. And so you do go back and forth. And they cancel out again because of the orientation. This one is kind of a cool problem. And they gave you this picture in there, and they gave you just a few values, a 3 there and a 2 there. So you kind of knew that this would be 3 and 3 or 6 wide. and this, I guess that's 5, so it's 10 there. So the area of the entire thing is like 6 by 10, and so on and so forth. But here's the thing. So they give you this. They give you the circulation around the circle happens to be 12. And then they want you to use Green's theorem to figure out what is the circulation then around this other thing. So I'm using something I know to figure out another piece that I don't know. And we're going to see how that happens. But what they tell me is I do know whatever the vector field is. And notice the vector field is nowhere mentioned in here. It's just an F there, it's an F there, and it has an F1 and an F2 in it. But that's all I get to know. And so they say, well, I'll tell you that the integrand in there for Green's theorem is -3. And so, and this should be an X right there. Or no, that should be an X. But, so anyway, then when we use this, we can say, all right, well, I know that the circulation around the whole thing should be the circulation around the first curve, and so we're walking this way, and we're walking this way, and when I do that, my left hand is inside, so this has the wrong orientation to it. So notice I put a minus there because it changes. Now, this piece, they already told me was 12. So in there, that's how I changed that to 12. Now, I know this. I know this integrand over here, so this is where I'm going to take this piece, and I'm going to change it out for Green's theorem, because they told me to use that. And I know that the integrand there is -3, so they gave me that piece. But if I have this, I can pull the 3 out, and then I have the integral of just 1, which is the area of that entire region, domain. And so what is the area of that? Well, the area of this thing would be, I said this is 10, because that's 5 and 5, and that's 3 and 3. So this is a 10 by 6 rectangle, that's 60. And then this is a 2 right there, so pi r squared is 4 pi. So that shaded region in there is 60 minus 4 pi. So I've got my -3. I now figured the area of the domain, and that -12 I can add to the other side. And notice what they wanted me to solve for. I can actually solve in there, add the 12, and then I can get the exact amount of that. That's really cool that they gave you, it's sort of like you're playing detective. You don't get to know the vector field. You only get to know part of that, the mixed partials and that difference in there. And then you have to kind of reason out that how would it work? And turns out little pieces you can keep replacing with certain things. So I'm going to stop there, guys, because it is going to get long. But that's the first part. I will make more of these going through the rest of the notes, and I hope this is helping, and I hope you can see. And I'm trying to very meticulously explain and show where and why everything came from and how you should be thinking about it in the moment. So I'm going to cut there, but I will be back in just a few minutes, and we will be going on to Stokes' theorem, which is Green's theorem in a dimension up. And so instead of a surface and a boundary being a curve, we now have a solid, and the boundary is a surface. And so, and this is where the curl is going to play in too. So I will come back there, but this is enough for Green's theorem and how you use Green's theorem to make life simpler with circulation, and when you don't know the vector field is necessarily conservative, because if it was, it's automatically 0. So Green's theorem is kind of dumb in the case that it's 0, but it should make sense to you, because if the vector field's conservative, then you know that df2 with respect to x equals df1 with respect to y. And if you took the df2 with respect to x and subtracted, because you had df1 with respect to y, if you subtract that to the other side, it's 0. And so knowing the vector field is conservative, Green's theorem still holds, and it kind of adds a layer of validity to why would it always be 0. But if the vector field's conservative, the cross partial property holds, and this is part of the cross partial property, just moved around. And but if it was conservative, that turns out to be 0, and so this would always be 0, and that's always circulation. And so in a conservative vector field, circulation is always 0. So there you see it again. All right. So like I said, I'm gonna cut here, and then I'll do another one on Stokes' theorem, and then I'll do a third one on divergence. All right. Take care, guys. Hang in there. Bye-bye.